Hello everyone, I am Rama Devi, Maths PGT from Gajpat Nagaram KGBV in Vizianagaram district. Today we have discussed circles. In circles chapter we have
and lambda. And in this case, frequency is equal to V by lambda. Enclosed in this pipe will disturb. So the way in which the disturbance occur, how the waves, standing waves formed in this type of pipes, organ pipes. This type of pipe is called closed organ pipe. Say for example sunlight. When you are blowing sunlight, and it is also nothing but closed organ pipe. Now let us see how these waves are formed in the closed organ pipe. See, we can consider this is a closed organ pipe. One side it is closed and the other side it is open. So this is the closed end and this is the open end. Suppose if it is enclosed with air molecules like this. Suppose if this is enclosed with air molecules like this at different positions in our consideration. There are, if you observe this particular position, this is open end. If you create a disturbance here, what happens? The degree of freedom is more, hence this can vibrate this way in the forward direction and reflected back and moves in the reverse direction, backward direction. So it moves in the forward direction. All the particles, they move in the forward direction. And as a result of that, every particle will move with a less displacement. See, this is very, very less. And almost its displacement become less. And the displacement of this becomes 0. So degree of freedom is very, very less, almost all 0 at this closed end. This is the closed end, closed side of the pipe. This is closed end. So the degree of freedom of the vibration of the molecules in the pipe are 0. That's why they cannot move. The net displacement of the particles lies on the closed end, almost all 0. So when you are imagining that when a disturbance is created, they move with what displacement? Since the particles lies at the open edge, open end of the pipe, they have more degree of freedom, hence they move with more displacement. So if you observe the displacement versus the position of the particles, so I just write down here, if this particle is moving in the x forward direction, I write here for this particular particles, the displacement in this direction is this one, and for this one will be somewhere here. It will be a little bit less than this, and for displacement this will be less, and for this, and for this, and for this 0. So if you imagine that this curve represents like this, so I just write down, this is the displacement of this one and this is the displacement of this one, and this is how in the positive x-axis. While they are coming back and they are reflected back, since this is a closed end and they reverse by 5 degrees of phase, and as they come back, and this is how they come back with increasing displacement. They just come back with increasing displacement and reverse by phase angle pi as they are reflected at a rigid boundary. So the degree of freedom is more at this end. That is why the displacement is more and they reversed by pi degrees of its phase. So you can just write down the displacement in the reverse way will be like this. and this will be like this, and you can just write down. This is the waveform under our consideration. So this is the waveform. Create a waveform like this, and this waveform has a wavelength of lambda by 4. So the length of this air column, in the first mode of vibration, it creates one antinode. This is antinode, and this is node. And this open end, always at open end, it forms antinode. Always at closed end, it forms node, because the degree of freedom is almost 0. And the degree of freedom to vibrate the particles at open end is maximum. That is why it forms antinode and node. So this is the minimum wavelength with which it can form a stationary wave, and which give a certain note. This note is called fundamental note, or the frequency corresponding to this first mode of vibration is called the fundamental frequency. So I just write down the length of this particular wave first mode of vibration is equal to lambda by 4. Therefore, the lambda in this case, first mode of vibration, is equal to 4L. So that is why the frequency corresponding to this particular first mode of vibration is called the fundamental frequency of closed organ pipe. So now let us derive the expression for closed organ pipe. Fundamental frequency of closed organ pipe. Fundamental frequency of closed organ pipe. Simply I write here closed pipe. So we know pretty well that velocity of sound is equal to L lambda, and in this case frequency is equal to V by lambda. So in the first mode of vibration, N is equal to V by, instead of lambda we can write down 4L. So the fundamental frequency is equal to, N is equal to V by 4L in case of a closed pipe. So this is the frequency with which the air column in the closed pipe, it vibrates, which is equal to 1/4 of the wavelength. That is why we can write down the fundamental frequency is equal to V by 4L. So this is what is called first harmonic. This frequency is called first harmonic. This is also called first harmonic. And now let us see what will be the next type of vibrations. In the same time, there is a possibility of occurring the different notes for the same given length. Let us see what will be the next stage of vibration. Now let us see. In the first case, we have already derived the frequency of the fundamental note in case of a closed organ pipe as N is equal to V by 4L. This is what we have derived. And in this case, there is one antinode and one node. And in the immediate second mode of vibration, there are two nodes. This is one node and this is another node. There is a second possibility with which it can vibrate. So what is the length of the air column? L is equal to 3 lambda over 4, 3 times lambda by 4. And hence lambda in this case is 4L by 3. Now let us see what will be the frequency corresponding to this second mode of vibration. In the second mode of vibration, second mode of vibration or this is also called first overtone. Always the first one is called fundamental frequency. This is fundamental mode. And the frequency corresponding to this is first harmonic. This is called first harmonic. And the second stage is second mode of vibration, this one, in which there are two nodes and there are two antinodes are formed here. So in this case, we want to find the frequency. I write here the first overtone N1 is equal to V by lambda. That is equal to, instead of lambda, we can write down 4L by 3. So this becomes 3 times V by 4L. Now you can write down the frequency. In this case, the second mode of vibration, first overtone frequency is equal to 3 times its fundamental frequency. So this is what is called the frequency of the first overtone and the third harmonic. This is what is called third harmonic. So we can write down this is first overtone or third harmonic. See, in the first we obtained first mode of vibration, we got first harmonic, and the immediate mode of vibration we are able to get only third mode. In this case, the second harmonic is absent. We cannot get the second harmonic in case of this closed organ pipe. So now let us see the third mode of vibration. In the case of third mode of vibration, in this case, how many nodes are there? 3 nodes are there. And how many antinodes are there? 1, 2, 3. 3 antinodes are there. Then what is the length of the air column? In this case, length is equal to 5 lambda by 4. So lambda is equal to 4L by 5. As you know, the frequency corresponding to this third mode of vibration, frequency corresponding to the third mode of vibration. In this case, we have 1, 2, 3. 3 nodes and 1, 2, 3. 3 antinodes, and length of the air column is 5 lambda by 4. Hence lambda is equal to 4L by 5. So we know that frequency is equal to V by lambda. But this is the second overtone. Third mode of vibration or second overtone. And now let us find the value of N2. Instead of lambda, you substitute here 4L by 5. We will get 5 multiplied by V by 4L. So in this case, N2 is equal to 5N. So we got fifth harmonic. This is what is called fifth harmonic. So I write here, in this mode, we got only fifth harmonic. So with the closed pipe, with the closed pipe, we will get only the fifth harmonic. All odd harmonics are available in case of the closed organ pipe. So in case of closed organ pipe, in the first mode of vibration, we get the first harmonic, that is fundamental frequency, and the second mode of vibration or first overtone, we get third harmonic. In the third mode of vibration, we get the fifth harmonic. So we get all odd multiples of the harmonics are available. All even numbered multiples of harmonics are not available. For example, sa, re is not possible. Ga, ma is not possible. So alternative, all odd multiples are available in case of this closed organ pipe. So the relation between the fundamental frequency and the different mode of vibrations is harmonics is equal to n is to n1 is to n2 is to n3 is to and so on is equal to 1 is to 3 is to 5 is to 7 is to and so on. So this is the first fundamental frequency, and this is first overtone or third harmonic, and this is the second overtone or fifth harmonic, and this is the third overtone or seventh harmonic. See, once you know, you want to find the frequency corresponding to the second overtone. So second overtone frequency is equal to 5n, 5 times of the fundamental frequency. So this is the ratio in case of the closed organ pipes. Now let us see what will be the fundamental frequency and other frequency of overtones in case of the open organ pipe. So the standing waves formed in open organ pipe. If the pipe is open both the ends, if a pipe is open both the ends, and this is open and this is also open. So if the pipe is open both the ends, the pipe is called open pipe. Now let us see, this is the open pipe. So we can consider that this is open pipe. See, both the sides kept open, and it has both the sides the maximum degree of freedom. So the molecules are the air particles in the medium, just they vibrate with maximum displacement at both the ends, whereas with the zero displacement at its center. So degree of freedom is at the center is 0, and the degree of freedom is increasing towards the edges, towards the open edge, open end. Now the degree of freedom at this is more, and it vibrates with maximum displacement, possible displacement. Hence, it forms at the edge is antinode. Similarly, here also it forms antinode, and the degree of freedom is more at the open end, and it just vibrates with the maximum displacement. And similarly, when you are going towards the center of the pipe, and the displacement will be decreased in the decreasing order, and the displacement will be decreased and finally become 0. And this is how when these two move in opposite directions, when this is moving in this way, this will come to this way. This way. This is how they move. So in this way, you just imagine this particular region is almost all formed node. And if you observe the graph, the displacement in this forward direction is gradually decreasing toward the center. So what happened now? The displacements are gradually decreasing in its order. So the maximum displacement at this particular position and the displacement is decreased, while come to this point again decreased, and almost all displacement becomes zero. And if you observe here, the displacement in the opposite direction, it is less, like this. And if you observe here, it just becomes a little bit more. And when you come to this end, in the opposite direction, it becomes more. This is how. And for another direction, it comes in the reverse way, like this. And you will be getting a wave like this. And the other end. So, this is how you will get a stationary wave in such a way with minimum one node and with two antinodes. So, this is how. This is the way in which they vibrate like this. And this particular region, they vibrate more. And when you come to this particular layer, the vibrations are just a little bit less than the first one. And while very close to the central region, the displacement is very, very less. And when it is exactly at center, the degree of freedom becomes zero and it forms a node. So, at the edges, we have antinodes. At the center, we have node. So, this is the minimum wavelength with which it forms the fundamental node. That is why the length of this pipe, I just write here, length of the air column is equal to lambda by 2. And this way we can write down lambda is equal to 2L. In this open argon pipe, this is the first fundamental mode of vibration. In this fundamental mode of vibration, we have two antinodes and one node. And the length of the air column vibrating in the pipe, in the first mode of vibration, it is possible with which the length of the air column is half of its wavelength. See, lambda is equal to 2 times of the length. Now we can find the fundamental frequency of this first mode of vibration. So, this is first mode of vibration. This is first mode of vibration in case of open argon pipe. This is also called fundamental mode. This is also called fundamental mode. And the frequency corresponding to this is called fundamental frequency. Fundamental frequency. So this fundamental frequency, according to the formula V is equal to N lambda, where velocity of the wave is equal to N lambda, where N is equal to V by lambda. But in the first mode vibration, lambda is equal to 2L. Therefore, fundamental frequency in the open pipe, N is equal to V by 2L. This is the formula for the fundamental frequency of the open pipe. This is also called first harmonic. This frequency is also called, this note is also called first harmonic or fundamental frequency. This is how the waves formed stationary or standing waves formed in the open pipe. Now let us see what will be the next mode of vibration immediately. At the same time we can listen for the same length with different notes. Let us see what will be the next second mode of vibration. That is also called the frequency corresponding to first overtone. Now let us see. Already we have discussed the fundamental frequency of open pipe is n equal to V by 2L. This is also called first harmonic. And now let us go to the next mode of vibration, that is second mode of vibration. In this mode, we have 1, 2, 2 notes and 1, 2, 3. 3 antinodes are there. So, the length corresponding to this air column L is equal to lambda or simply 2 lambda by 2. So, this is 1 lambda by 2 and this is another lambda by 2. So, 2 lambda by 2, L is equal to lambda. So, we know the frequency is equal to V by lambda. But N is equal, I write here, this is frequency corresponding to first overtone. That is why I write here N1. N1 is equal to V by lambda. So, that is equal to V by, in this case, lambda can be written as 2 times to the of 2L. So, this frequency N is equal to 2 times of fundamental frequency. So, this is what is called the second harmonic. This is what is called second harmonic. So, second mode of vibration corresponds to first overtone, or we can also write down this as second harmonic. Now, so second harmonic is available in the case of open pipe, but second harmonic is not available in case of closed pipe. That is the difference between these two. And in the third mode of vibration, if you observe, this is what is called second overtone. In this case, you see the degree of freedom is always maximum at both the ends. So here it forms antinode and node, antinode, node, antinode, node, and antinode. So 1, 2, 3, 4 antinodes and 3 nodes are formed in this case. And length of the air column is equal to 3 lambda by 4. This is 1 lambda by 2 and this is another lambda by 2 and this is another. So 3 lambda by 2. There are 3 lambda by 2. So lambda is equal to 2L by 3. You know, the second overtone frequency is equal to V by lambda. So that is equal to V by, you can write down lambda is equal to 2L by 3. So I write here, this is 3 times V by 2L. 3 times V by 2L. So N2 frequency of the second overtone is 3 times the fundamental frequency. So this is what is called third harmonic. This is what is called third harmonic. Third harmonic. So in case of open organ pipe, we can get all harmonic, integral multiples of all harmonics are available. First harmonic, second harmonic, third harmonic, fourth harmonic. This is first harmonic, this is second harmonic, and this is third, 4, 5, 6, and so on. Just like in a stretched string. So you can, all notes are available. Sa, Re, Ga, Ma, Pa, Da, Ni, Sa. Every, without missing any note. So almost all notes are available in case of the open organ pipe. Now let us see the difference among stretched strings and open pipe, closed pipe. the ratios of frequencies, fundamental frequencies to the immediate overtones in case of open organ pipe. N is to N1 is to N2 is to N3 is to and so on is equal to 1 is 2 is to 3 is to 4 and so on. So all integral multiples of the harmonics are available in case of the open organ pipe. This is similar to that of the stretched string in. This is similar to that of a stretched string. In a stretched string, the fundamental frequency is equal to 1 by 2L under root to T over mu. So the fundamental frequency, and in the case of stretched string, see these two, the length is equal to lambda by 2. Length is equal to length of the string, the length of the air column in this case. So just you compare these two. In case of second mode of vibration, for the same length, there is a possibility of formation of the string with two loops. So in this case, the first overtone is equal to 2 times to that of the fundamental frequency. In this case, lambda is equal to L equal to lambda. This is the second mode of vibration or first overtone. Then you compare these two, which are equal. And now let us go to the third mode of vibration, where you will be getting one node, this is how, 3 loops. Here you are getting 3 loops. So length corresponding to this is 3 lambda by 2. And the frequency corresponding to this is 3n. So just like in an open organ pipe, you can compare this with the frequencies in stretched strings. So even in stretched string, you have fundamental frequency to its overtone frequencies are in the ratio 1 is to 2 is to 3 is to 4. That means all harmonics are available in case of the stretched string and in case of open organ pipe. But in case of the closed organ pipe, only in closed organ pipe, the frequency ratio n is to n1 is to n2 is to n3 is equal to 1 is to 3 is to 5 is to 7 and so on. So only odd multiples of harmonics are available in case of closed organ pipe. So these are the different differences observed in case of the stretched string. As far as compared with stretched strings are almost all equal to that of open organ pipe, and in case of closed organ pipe we will get only odd multiples of harmonics. Now you carefully listen the comparative observation in case of stretched string, open pipe and closed pipe. See, in this case, fundamental frequency is equal to 1 by 2L under root T over mu, tension and linear density of the wire. In this case, velocity of sound in air by length of the air column. This is in case of open pipe, V by 2L. And in case of closed pipe, fundamental frequency is equal to V by 4L. So this is the related figure. The first overtone, in case of stretched string, it is also second harmonic. N1 is equal to N. In case of the open pipe, N1 is equal to N. So both are same. And in case of closed pipe, there is no presence of second harmonic. Directly we are obtaining third harmonic immediately after fundamental frequency. So there is no possibility of getting the even numbered harmonics in case of this closed pipe. And in case of open pipe, we can get all the integral multiples of the frequencies. Even also it is true in case of stretched strings. So in case of closed pipe, in the second overtone, N2 is equal to 3N. This is the third harmonic. This is also third harmonic. And in this closed pipe, you don't get fourth harmonic. Immediately you will get fifth harmonic. So this is all the comparative observations of the three types of the stationary waves formed in three: stretched string, open pipe, and closed pipe. Now let us find the velocity of sound in air using resonance tube. See, we can use the resonance tube. This is what is called resonance tube. It is of 1 meter long pipe which is transparent, and this is to be filled with water, and this is open one side and closed the other side, connected to a rubber tube, and the another end of the rubber tube connected to a reservoir. So the reservoir is filled with water along with the tube. What is this? Resonance tube. And this resonance tube has mounted with a 1 meter scale, and all these arrangement connected to a vertical stand. And now, if a tuning fork is just excited or hit with a rubber hammer and keep horizontally as shown in the figure, then what happen? The vibrations of the tuning fork, will just create a disturbance in the air column of this tube. This is the air column. Up to this particular part is air column. This air is filled in this. This air start vibrations, and when the tuning fork is excited in the tube, if the frequency of this is N, the natural frequency of the tuning fork is N, then it creates a disturbance in the resonance tube. The air in the resonance tube produce a stationary wave. The first mode of stationary wave, L1 is lambda by 4, as we know. L1 is lambda by 4. And the frequency corresponding to the vibrations of this air column and the natural frequency of the tuning fork, when these two become equal, you will get a loud sound. This situation is called resonance. The natural frequency or the fundamental frequency, first mode of vibration of the air column with which it is vibrating, and the natural frequency of the tuning fork, when they become equal, then the phenomenon of resonance occurs. So the sound vibrates with maximum amplitude. This particular stage is called resonance. So in the first resonance condition, we will get the length of the air column. So the length of this air column can be measured by lowering the reservoir or moving up the reservoir. You can change the liquid level in the resonance tube. So this particular length, say at a particular stage, you will get the first mode of vibration, and it gives a loud sound. This is called resonant sound, and the length corresponding to this air column. We can obtain this with the help of the scale fixed at the adjacent side to that of this tube. So the length of this air column can be measured, L1. Say for example, L1 is 16 centimeters. And immediately if you lower the reservoir, you can decrease the level of the water in the tube, and at a particular position you will be getting another stage where you will get loud sound. In this case, we will be getting a stationary wave like this. You will be getting a loud sound. So this length is corresponds to L2 is equal to 3 lambda by 4. This length. So in the first length, you are getting one resonance sound, a loud sound, and at the second stage immediately, the successive loud sound will occur at 3 lambda by 4. Suppose if it is L1 is some 16 centimeters, then at what position it will occur at 48 centimeters. At immediately 48 centimeters, you will be observing a loud sound. So there are two successive resonating sounds. So the difference between these two lengths, L1 is equal to lambda by 4, L2 is equal to 3 lambda by 4, and L2 minus L1 is equal to lambda by 2. So lambda is equal to wavelength in this air column is equal to 2 into L2 minus L1. As you know, velocity of sound is equal to n lambda. So V is equal to 2n into L2 minus L1. Now, using this formula, we can determine the velocity of sound in air at room temperature. See, what is this n? This is the natural frequency of this tuning fork. Say this tuning fork may have some value such as 512 Hz. So once you know the value of this frequency, n is equal to 512 Hz, L1 is equal to 16 centimeters, L2 is equal to 48 centimeters, then it is very easy to find the velocity of sound in air. V is equal to 2 into where n equal to 512 into what is L1, L2? L2 is 48. L2 is 48 centimeters minus L1 is how much? 16 centimeters. So this comes 2 into 512 into 48 minus 60 is equal to 32. So this comes the value around. Now this value becomes 32,768 centimeters per second. So this is equal to 327.68 meters per second. This is how we can determine the value of the velocity of sound in room temperature. And now let us see actually the waves formed not exactly from the open end. The stationary wave will form a little bit above the open end. So we have to measure this. We are not measuring this particular part of the length. Now we have to consider this as E. This is the part above the open end which is not taken into consideration. We are just considering only the wave from its open edge. We are measuring the length of the air column. But it is not like that. The air column will form just a little bit above the open end of the tube. So we have to take this also into consideration, E. This is what is called end correction. This end correction is equal to, E is equal to, say for the first one, this is L1 plus E. For the first one, L1 plus E is equal to lambda by 4. In the second case, L2 plus E is equal to 3 lambda by 4. So for length L1, you have to add E, that is equal to lambda by 4. For the second stage of resonance air column, we have to consider L2 plus E, that is equal to 3 lambda by 4. And if you just take the equation for lambda and just you eliminate lambda, you will get E is equal to L2 minus 3L1 by 2. This is what is called the end correction. Then this is equal to 0.61 times the radius of the inner radius of the tube. This is the radius of the tube, this particular part. This is the radius of the tube, inner radius of the tube. So the end correction is equal to 0.61 times the radius, inner radius of the tube. This is for this open end. This is what is the end correction in case of closed pipe. If it is in case of open pipe, we have to consider both the sides, and the end correction will become twice to that of the end correction existed in the closed pipe. So in case of this, we are getting end correction is equal to 0.61 times the radius, inner radius of the tube. This is how we have to determine the end correction of the resonance apparatus. Now let us solve one problem. You see, a vertical tube is made to stand in water so that the water level can be adjusted. Sound waves of frequency 320 Hz are sent into the top of the tube. If standing waves are produced at two successive water levels of 20 centimeters and 73 centimeters, what is the speed of sound waves in air in the tube? So first of all, you have to understand that a tube can be adjusted in water. A vertical tube made to stand in water so that the water level can be adjusted. So you can just keep the tube like this. So the water level can be adjusted by dipping it or by raising. And now when a tuning fork is hit here with what frequency? 320 Hz. 320 Hz. Then what happened? First of all, a standing wave is formed at what level? 20 centimeters. And the next resonating stage occur at 73 centimeters. Then we have to determine the velocity of sound or speed of sound in the air. So first of all, while solving the problem, we have to see what is the data given and what are the units given. This is most important. So we have to convert always the units into SI system. So the given data is the frequency of the tuning fork is given 320 Hz. This is SI unit. And L1, L2. L1 is given in centimeters, but we have to convert this into meters. So this can be written as 20 into 10 power of minus 2 meters. And again the second length is equal to, we have to convert this into meters, 73 into 10 power of minus 2 meters. Then what you have to determine the speed of sound in air column, air. So what is the necessary formula you require? The second stage is formula. So velocity is equal to 2n into L2 minus L1 is the formula. Then what you have to do, the next stage is, final stage is, you have to substitute and you have to calculate the value. V is equal to 2 times the frequency of the tuning fork is given 320 multiplied by L2 minus L1, 73 into 10 power minus 2 minus 20 into 10 power of minus 2. Now after simplification, you will be getting 33,920 centimeter into 10 power of minus 2 meter per second. We already converted into meter per second. So what is the value of this? 339.2 meters per second is the velocity of sound in this case in the tube. So this is how we have to solve the problem. And now let us see the next problem regarding open pipe and closed pipe. Now let us see the another problem. A closed organ pipe 70 centimeters long is sounded. If the velocity of sound is 331 meters per second, what is the fundamental frequency of vibration of a air column? So in this problem, we have to observe the given data. Length of the air column is given. It's a closed pipe. It is a closed pipe. And for a fundamental frequency, we have to observe the first mode of vibration. So this is the first mode of vibration for which length is given. How much? 70 centimeters. But this is given in CGS system, whereas velocity is given in SI units. So we have to convert this into meters. 70 into 10 power of minus 2 meters. See, there is a common mistake everybody is doing. Directly they substitute the value, but we have to see, always we have to convert the units into a common unit, that is SI unit. So the centimeter is to be converted into meter. V is given 331 meter per second, and we have to determine the frequency. So what is the formula related to this closed pipe fundamental frequency? N equal to V by 4L. In this case, N is equal to V by 4L. That is the formula you have to write. And calculation, substitution and calculation. So the velocity is given 331 meters per second by 4 times its length. That is comes 118.2 H. You have to mention the unit is most important. Without unit for a physical quantity, there is no meaning, and you have to see that you should be very particular about the applying the proper unit. So this is the one type of problem. Now let us see another problem. Say in this problem, a metal bar when clamped at its center resonates in the fundamental frequency with longitudinal waves of frequency 4 kHz. If the clamp is moved to one end, what will be its fundamental resonance frequency? Say in the first case, a clamp is set at the center of the wire and the longitudinal waves are produced. And when it is set at the center, it can be considered like this, and the length of the wire will be equal to half of the wavelength. So lambda is equal to 2L in this case, and the frequency of vibration of this is equal to longitudinal wave is equal to V by L, that is equal to V by 2L, that is given 4 kHz. And in the next case, the clamp is moved to one end, the another end. Then what happens? It just behaves like closed pipe. So in this case, the fundamental frequency is equal to V by lambda dash, new one. This is lambda dash. So I write here lambda dash. So this can be written as V by 4L, because lambda dash is 4L. But we can write down this half of V by 2L. Therefore, this becomes 2 kHz. So the frequency reduced to half by shifting this clamp to another end. So this is the way in which we can solve this type of problem. Now there is one more problem. A string has a length of 0.4 meters and a mass of 0.16 grams. If the tension in the string is 70 newtons, what are the 3 lowest frequencies it produces when plucked it? So this is the problem given, and now we have to observe that a string is to be plucked. When it is plucked, the lowest frequency is the fundamental frequency, that is N is equal to 1 by 2L under root T by mu. And we have to find the next immediate frequency. The next immediate frequency is with 2 loops. So this is the next frequency with which it vibrates. If the frequency of this is N, this frequency is 2N. And the third one is, we have to observe that it it has to vibrate with 3 loops. So it has to vibrate with 3 loops like this. And its frequency is 3n. So in general, for any number of loops, p loops, 1 loop, 2 loops, 3 loops and so on, p loops, then the frequency can be written as p by 2l into under root t over mu. This is the general formula for any p loops. But here, when the string is plucked, what is the length of the string? It is given 0.4 meters. What is the mass of the total string? 0.16 grams. See, it is given grams. This is CGS unit. You have to convert this into MKS unit immediately. So we have to write down this as 0.16 into 10 power of minus 3 kilograms. Immediately you have to convert this into kilograms. And tension is given in newtons, 70 newtons. So now we have to find the linear density. Linear density of the string is equal to total mass by total length. Total mass by total length is equal to 0.16 in 10 power minus 3 kilograms by total length is 0.4. So you will be getting the mass per unit length. That is the linear density. So what is the mass per unit length? 0.4 in 10 power minus 3 kilogram per meter. Every meter wire has a mass of 0.4 into 10 power minus 3 kilograms. Now, we are going to the 3 lowest frequencies. The 3 lowest means first fundamental frequency, next immediate first overtone, and then second overtone, or first harmonic, second harmonic, third harmonic. So what is the first fundamental frequency? 1 by 2L root over T by mu. So now let us substitute the value. 2 into 0.4 is the length in meters under root 70 in newtons by in kilograms per meter. So all these are in SI units. So the final answer is 523 H. So once you know the fundamental frequency, you can express in terms of the overtones, because all the integral multiples of the fundamental frequency will give the next immediate harmonic or the overtones. So the next second lowest one, first lowest, second lowest is the first overtone, that is equal to 2n, 2 into fundamental frequency. So you are getting 1046 H. And the next, the third one n3 is equal to 3n. So 3 into 523. So 1569 H. So these are the 3 frequencies, lowest frequencies you can obtain by stretching this string.
Hello everyone, I am Rama Devi, Maths PGT from Gajpat Nagaram KZBV in Vizianagaram district. Today we have discussed circles. In circles chapter, we have to discuss the position of the point and power of the point and the length of the tangent and etc. Before we discuss the topics, we should write down the important notations. For example, say S is equal to, represented as circle, x square plus y square plus 2gx plus 2fy plus c. You know it is represented as circle, S is equal to, and S1 is equal to xx1 plus y1 plus g into x plus x1 plus f into y plus y1 plus c is equal to 0. This is called S1. Now S11 S11 means x1 square plus y1 square plus 2gx1 plus 2fy1 plus c is equal to 0. S12 x1 x2 plus y1 y2 plus g into x1 plus x2 plus f into y1 plus y2 plus c is equal to 0. These are very important notations. So ఇవన్నీ కూడా మీరు నోట్స్ లో నోట్ చేసుకోండి. S1, S11, S12. Now let us discuss position of a point. What is that means? Position of a point. We need to locate the point with respect to the circle. For example, we take a circle and same circle. So the position of point with respect to the circle, at three locations. First, say if this is s is equal to 0. Here we take P, x1, y1. We take any point P. So P lies on the circle and P lies inside the circle and P outside the circle. These are three locations. P lies on the circle and P inside of the circle, P outside of the circle. So how to locate the position of a point? So S11, we take S11. S11 ante if S11 is equal to 0. If S11 is equal to 0, then P lies on the circle. S11 is equal to 0 అయితే P అనే పాయింట్ సర్కిల్ పైన ఉంటుంది. And if S11 less than 0, P inside of the circle. P lies inside of the circle. And if S11 greater than 0, P lies outside of the circle. Here we talk about tangent. We can draw tangent through P, one tangent. Here number of tangents. Here we can draw number of tangents through P, only one. Here any number of tangents can we draw? We cannot draw. So here number of tangents 0. Here how many tangents can we draw? This from point P, this is one tangent and this is another tangent. So two tangents. Here two tangents we can draw from P to the circle. Here number of tangents 2. Here we have an example. How to locate the point. How to locate the position of the point with respect to the circle. So for example, one problem. Locate the position of the point 2, 4 with respect to the circle x square plus y square minus 4x minus 6y plus 11 is equal to 0. So, ఈ సర్కిల్ కి ఈ పాయింట్ ఆన్ ది సర్కిల్, పాయింట్ సర్కిల్ పైన ఉందా లేదా సర్కిల్ లోపల ఉందా లేదా అవుట్ సైడ్ ఆఫ్ ది సర్కిల్ ఉందా మనం కనిపెట్టాలి. సో అలా కట్టాలి అంటే ఫస్ట్ we have to do S11. S11 means x1 square plus y1 square plus 2gx1 plus 2fy1 plus c. So here x1, y1 means given point x1, y1. x1 square, 2 square, y1 square, 4 square 2g x1. Here x1 coefficient, x coefficient same. So 2z minus 4. So minus 4 into x1 means 2 plus 2f means minus 6. So minus 6 into y1 means 4 plus c 11. So this is 4, 4, 4, 16, 4 2s, 8, 24 plus 11. This is simplified minus 1. So S11 is equal to minus 1. This is less than 0. So S11 less than 0. We know if S11 less than 0, where is the location of the point? Yes, inside of the circle. The point, given point inside of the circle. Therefore, P lies inside of the circle. Now, the power of a point. What is power of a point? The definition is S is equal to 0 is the equation of the circle C, and C is the center with the center C and radius R. Let P x1 y1 be any point in the plane, then Cp square minus R square is defined as power of the point P with respect to the circle. That means, so this is S is equal to 0 circle. This is center P. So P, this is P. This is radius. This is called radius. And also distance between CP. So CP is here. CP square is equal to R square. CP is equal to R. Here P, if P lies on the circle, Cp square is equal to R square. So this is Cp square minus R square is equal to 0. So in case of here P, this is radius and this is Cp. Cp is less than R. Cp square less than R square. So Cp square minus R square is less than 0 here. Here Cp square minus R square greater than 0. So Cp square minus R square is called power of a point. Here Cp square minus R square means we also Cp square minus R square is also written as S11. So S11 notation is very important to location of the position of point and power of the point. S11 అనేది position of point కనుక్కోవడానికి, power of a point కనుక్కోవడానికి కూడా S11 చాలా important. For example, one example, find the power of the point P 2, 3 and S is equal to x square plus y square minus 2x plus 8y minus 23 is equal to 0. To find the power of the point S11, we have to find out S11. S11 means another again x1 square plus y1 square plus 2gx1 plus 2fy1 plus c. This is equal to x1 y1 means x1 y1, x1 square 2 square plus 3 square, x1 square y1 square 2 square 3 square minus 2 x1 means plus 8 into y means 3 minus 23. This is equal to 2 2's 4, 9 minus 4 plus 24 minus 23. We simplify that. This is equal to 10. So S11. The power of the point is S11 is equal to 10. ఇది 2 marks question. Next. Now, length of the tangent. What is the formula of length of the tangent? This is a circle. S is equal to 0. Center C. We take P, x1, y1, any point on the plane. We draw from P to the circle a tangent. This is called a tangent which touches A. From P to the circle we can draw the tangent which touches A. Then PA is called the length of the tangent. So here the length of the tangent PA is equal to root S11. For example, find the length of the tangent from P to 5 and S is equal to x square plus y square minus 5x plus 4y minus 5. To find out the length of the tangent, we have to find out S11, root S11. S11 is equal to same x1 square plus y1 square plus 2gx1 plus 2fy1 plus c. S11 x1 square 2 square 5 square minus 5 into 2 plus 4 into 5 minus 5. This is 2 square 4, 25 minus 10 plus 20 minus 5. We simplified 34. But length of the tangent formula root S1. So length of the tangent is equal to root S11. This is root 34. This is the answer. Another example about length of the tangent. If a point P is moving such that the lengths of the tangents drawn from P to the circles. So ఇక్కడ 2 circles ఇచ్చాడు. కండిషన్ ఏంటి? The lengths of the tangents drawn from P to the 2 circles are in the ratio 2:3. For example, PT1 and solution. PT2 be 2 lengths of the tangents. But given the lengths of the tangents are in the ratio 2:3, that means PT1 divided by PT2 is equal to 2/3. It becomes 3 times of PT1 is equal to 2 times of PT2. So PT1 means the length of the one tangent, that is called root S11. Root S11. Finally we have to find out the equation of the locus of P. So we have to find out locus of P. Let P be any point on the locus. Let P be any point on the locus. P means x1, y1. So PT1 means root S11. 3 times of root S11 means 3 times of root S11. Here point P x1 y1 and circle x square plus y square minus 4x minus 6y minus 12. So x1 square root S11 means x1 square y1 square minus 4x1 minus 6y1 minus 12 is equal to 2 times of here PT2 another length of the tangent 2 times of another given circle x1 square y1 square 6x1 plus 18y1 plus 26. So squaring on both sides, we have 9 times of x1 square plus y1 square minus 4x1 minus 6y1 minus 12 is equal to square cheste 4 into x1 square y1 square plus 6x1 minus 18y1 plus 26. Here 9x1 square plus 9y1 square minus 9 4 36x1 minus 9 6 54y1 minus 12 is equal to 4x1 square plus 4y1 square plus 24x1 plus 4 18 72y1 plus 4 6. So 9x1 square 4x1 square 5x1 square plus 9y1 square 4y1 square 5y1 square minus 36x1 24x1 minus 60x1 minus 126y1. Here 108. So 108 104 212 is equal to 0. Therefore the locus of the point P is 5x square plus 5y square minus 60x minus 126y minus 212 is equal to 0. This is the answer. First, we have to find out the length of the chord. What is chord? This is circle. Center C. This is secant line. A line which cuts the circle at 2 points is called secant line. This is secant line, and AB is called chord. AB is called chord. So we draw from center to the perpendicular line to the secant line and join C, B and join C, A. We know this is the radius R and this is also radius. So the distance, perpendicular distance C, CM, this is called D. So we have to find out length of the chord. Length of the chord means AB. AB is equal to, M is the midpoint of AB. So BM plus MA is equal to AB. Length of the chord. Length of the chord కావాలంటే BM కనుక్కొని 2 times of BM చేస్తే length of the chord వస్తుంది. So ఇప్పుడు చూడండి. So this is right angle triangle. So from Pythagoras theorem, BM square is equal to R square minus D square. So BM is equal to root over R square minus D square. So M is the midpoint of AB. So AB, length of AB is equal to 2 times of BM. This is equal to 2 times of root over R square minus D square. So the length of the chord equation 2 into root over R square minus D square. Let us one example. For example, find the length of the chord intercepted by the circle x square plus y square minus 8x minus 2y minus 8 is equal to 0. So length of the chord kattali ikkada. Length of the chord. Solution. Length of the chord, formula 2 into root over R square minus D square. So here we have to find out R, radius in the circle, and D. D means perpendicular distance from center to the line. C. This is D. This is R. So D means the distance from perpendicular distance from center to line. So length of the chord 2 into root over r square minus d square. R means radius. So given circle x square plus y square minus 8x minus 2y minus 8. Here we have to find out center. Minus g minus f. So 2z place lo emundi 2z is equal to minus 8. 2f is equal to minus 2. C is equal to minus 8. G is equal to minus 4. F is equal to minus 1. C is equal to minus 8. Center. Minus G minus F is equal to minus G, minus of minus plus 4 minus F plus 1. This is the center of the given circle. Now R is equal to, we have formula G root over G square plus F square minus C. This is equal to root over G square 4 square plus F square minus C, minus of minus plus 8. This is equal to 16 plus 1 plus 8. This is root 25. This is equal to 5. R is equal to 5. Now we have to find out D. Now we have to find out perpendicular distance. We have a formula perpendicular distance from point P to the line modulus of ax1 plus by1 plus c by root over a square plus b square. Inter first year lo first 1b లో ఫార్ములా ఉంటుంది. Perpendicular distance from one point to the circle. ఈ డిస్టెన్స్ కట్టాలి అంటే ఈ పాయింట్ ఇది x1 y1, this is ax plus by plus c equal to 0 అయితే the distance d is equal to modulus of ax1 plus by1 plus c by root over a square plus b square. So ax1, so this is the line x plus y plus 1. So ax1 plus by1 plus c is equal to 0. This is the secant line, and c, we know c center c minus g minus f is equal to 4 1. So ax1 means a means x coefficient 1 into x1 plus b means y coefficient 1 plus c 1 by root of where x coefficient 1 square, y coefficient b 1 square. This is equal to 4 plus 1 by root 1 plus 1 2. So 4 plus 2 6 by root 2. This is the perpendicular distance d. So length of the chord formula 2 into root over r square minus d square. 2 into root over r square. We already find r square 5 square minus d square. D square means 6 by root 2 whole square. 2 times of 25 minus 36 by 2. Root 2 whole square 2. So 18. This is equal to 2 into root 7. This is the length of the chord. So position of a straight line. We have already the position of a point. Now we have to discuss the position of a straight line. Here also 3 cases. A line which touches the circle and a line which meets at 2 points in the circle and a line does not meet the circle. here also three cases. Position of a straight line. A line which touches the circle is called tangent, and a line which meets at 2 points, and a line which does not meet the circle. And another concept, the condition for a line to be a tangent. ఒక సర్కిల్ కి ఒక లైన్ టాంజెంట్ అవ్వాలంటే కండిషన్ ఏంటి? Now we take x square plus y square is equal to r square. This is circle. And y is equal to mx plus c. This is a straight line. ఈ సర్కిల్ కి ఈ స్ట్రైట్ లైన్ టాంజెంట్ అవ్వాలంటే కండిషన్ ఏంటి? The condition is c square by 1 plus m square is equal to r square. This is the condition for tangent to a circle. ఒక సర్కిల్ కి ఒక స్ట్రైట్ లైన్ టాంజెంట్ అవ్వాలంటే కండిషన్ c square by 1 plus m is the slope of the straight line. 1 plus m square is equal to r means radius of the circle, r square. And another concept, c square by 1 plus m square is equal to r square. So c square is equal to r square into 1 plus m square. C is equal to plus or minus r into square root cancel అయిపోతే root over 1 plus m square. C is equal to plus or minus r into root over 1 plus m square. So the straight line can be tangent. The tangent is y is equal to mx plus c. C means plus or minus r into root over 1 plus m square. This is the tangent of the circle with slope m. Y is equal to mx plus or minus r into root over 1 plus m square. This is the tangent equation. ఇది దేనికి? x square plus y square is equal to r square అనే సర్కిల్ కి. బట్ ఇంకొక సర్కిల్ s is equal to x square plus y square plus 2gx plus 2fy plus c is equal to 0 అనే సర్కిల్ కి టాంజెంట్ అవ్వాలంటే టాంజెంట్ ఈక్వేషన్. హియర్ సెంటర్ 0 0, బట్ హియర్ సెంటర్ minus g minus f. So y means, so transformation of axis 1b లో transformation of axis లో మనం ఏ రాసాం? x is equal to x plus h, y is equal to y plus k. ఎలా రాసామో ఇక్కడ కూడా అంతే. y coordinate y plus f is equal to m into x plus g plus or minus r into root over 1 plus m square. This is the tangent equation at x square plus y square plus 2gx plus 2fy plus c is equal to 0. So ఇది గుర్తుపెట్టుకోండి. y plus f is equal to m into x plus g plus or minus r into root over 1 plus m square. For example, find the equation of tangents to x square plus y square minus 4x plus 6y minus 12 is equal to 0 which are parallel to one straight line. So మనం find the equation of tangents. Two tangents equations కట్టాలి. ఎటువంటి tangents అవి? వేరొక స్ట్రైట్ లైన్ కి ప్యారలల్ గా ఉన్నాయి. సో దిస్ ఈస్ ది టాంజెంట్ అండ్ దిస్ ఈస్ ది టాంజెంట్. సో మనం ఇవి కట్టవలసిన టాంజెంట్స్. ఈ టాంజెంట్స్ రెండు వన్ స్ట్రైట్ లైన్ కి ప్యారలల్ గా ఉన్నాయి. అనదర్ స్ట్రైట్ లైన్, దిస్ ఈజ్ x plus 2y minus 8 is equal to 0. So if two straight lines parallel, the slopes are equal. So the slope of the straight line is minus x coefficient by y coefficient. So minus 1 by 2. So m is equal to minus 1 by 2. Find the equation of tangent means equation of tangent formula y plus f is equal to m into x plus g plus or minus r into root over 1 plus m square. So ఇందులో f కనిపెట్టాలి, g కనిపెట్టాలి, r కనిపెట్టాలి. So given circle 2z is equal to minus 4. So g is equal to minus 2. 2f is equal to 6. F is equal to 3. C is equal to minus 12. So R is equal to root over G square plus F square minus C is equal to root over G square. Minus 2 whole square means 4 plus F square 3 3 is 9 minus C minus of minus 12. So this is equal to 16 plus 9 is equal to root 25. This is equal to 5. R is equal to 5. So G is equal to minus 2, F is equal to 3, R is equal to 5. Now we substitute these values in the equation y plus f. Y plus f is equal to 3. చూడండి ఇక్కడ ఎప్పుడు కూడా మైనస్ జీ మైనస్ ఎఫ్ కట్టేవాళ్ళు మీ సెంటర్. సో ఇక్కడ కట్టనవసరం లేదు, ఓన్లీ జీ ఎఫ్ లు కడితే సరిపోతుంది. సో వై ప్లస్ ఎఫ్, ఎఫ్ మీన్స్ 3. y plus f is equal to m into m is equal to minus 1 by 2 into x plus g. X plus g is equal to minus 2. So x minus 2 plus or minus r into 5 into root over 1 plus m square. M means minus 1 by 2 whole square and 1 by 4. So y plus 3 is equal to minus 1 by 2 x minus 2 plus or minus 5 root 5 1 4 1 4 plus 1 5 5 by 4. Root 5 by 4 means root 5 by root 4 means 2. So here ikkada 2 ikkada 2. So it comes to 2 into y plus 3 is equal to minus x minus into minus plus 2 plus or minus 5 root 5. So 2y plus 6 is equal to minus x plus 2 plus or minus 5 root 5. Finally x plus 2y. So plus 6 minus 2 plus 4 plus or minus 5 root 5 is equal. So plus or minus ఎందుకంటే ఇక్కడ 2 tangents కనుక్కోమన్నట్ల ప్రాబ్లం లో find the 2 tangents. Tangents plus తో ఒక tangent minus తో ఒక tangent. X plus 2y plus 4 plus 5 root 5 is equal to 0 and minus 5 root 5 is equal to 0. These are the equations of 2 tangents. Equation of tangent at a point on the circle. So in that equation of tangent అది పాయింట్ ఇవ్వకుండా టాంజెంట్ ఈక్వేషన్ కట్టడం. ఇక్కడ ఒక పాయింట్ ఇచ్చి టాంజెంట్ ఈక్వేషన్ కట్టాలి. So equation of tangent at a point on the circle, formula S1 is equal to 0. Equation of tangent అని అడిగితే పాయింట్ ఇచ్చి టాంజెంట్ ఈక్వేషన్ అడిగితే ఫస్ట్ we have to find out S1 equal to 0. For example, one problem. Find the equation of tangent to x square plus y square minus 2x plus 4y minus 12 is equal to 0 at one point. So S11 ఇప్పుడు కాదు, S11 notation ఫస్ట్ బిగినింగ్ లో చెప్తాను. x1 plus y1 plus g into x plus x1 not 2g. g into x plus x1 plus f into y plus y1 plus c is equal to, so plus c. This is equal to x1. Here x1 y1 given point x1 y1. So S11 కాదు, S1 is equal to S1 equal to 0. S1 equal to x into x1 minus 1 plus y into 1 plus g into, here 2z is equal to minus 2. So g is equal to minus 1. So g anta minus 1. Minus 1 into x1 minus 1 plus f into 2f is equal to plus 4. So f is equal to f into 2 into y plus y1 means 1 plus c means c minus 12 minus 12. This is equal to 0. Equation of tangent kada. Minus x plus y minus x plus 1 plus 2y plus 2 minus 12 is equal to 0. Minus x minus 2x plus y plus 2y plus 3y plus 1 plus 2 plus 3 minus 12. So minus 9 is equal to 0. So multiplied with minus 2x minus 3y plus 9 is equal to 0. This is the tangent of equation. It's very important. 2 marks ki tangent equation eppudu adugutu untadu. Tangent equation, find the tangent equation at a point and iste matram s1 equal to 0 kattali. Okay. So here one more example of to find out the tangent equation. Find the equation of the tangent to one circle and given at point 3 minus 1, and also find the equation of tangent parallel to it. So first we have to find out the equation of tangent. S1 equal to 0. So given point P, x1 y1 is equal to 3 minus 1. So S1 equal to 0. S1 equal to S1 notation. What is the S1 notation? Xx1 plus yy1 plus g into x plus x1 plus f into y plus y1 plus c. So here we have to find out g and f. 2g is equal to minus 2 and 2f is equal to plus 4. So here c is equal to 0. G is equal to minus 1 and f is equal to 2, c equal to 0. Finally s1 equal to x1 x into x1 means 3 plus y into y1 means minus 1 plus g into, so minus 1 into x plus x1 3 f into plus 2 into y minus 1 plus c equal to 0, so equal to 0. This implies 3x minus y minus x minus 3 plus 2y minus 2 into 1, 2. This is equal to 3x minus x, 2x minus y plus 2y plus y minus 3 minus 2 minus 5 is equal to 0. This is the one tangent equation. But another tangent equation, we have to find out another tangent equation. What is the condition? Parallel to it. So, దీనికి parallel గా ఉండే tangent equation. So, if two lines parallel, the slopes are equal. If two lines are parallel, so the slopes are equal. So, దీని slope required tangent slope equal. So, దీని slope equal కాబట్టి, what is the slope of this tangent? M is equal to minus x coefficient minus 2 by y coefficient 1. This is equal to minus 2. So the equation of required tangent is, so slope form y plus f is equal to m into x plus g plus r into root over 1 plus m square. Here we have to find out r. R is equal to root over g square plus f square minus c is equal to root over g square 1 square plus f square That means 2 square 4. C equal to 0. So 0. R is equal to root 5. So substitute these values. Y plus F. Y plus 2 is equal to M. M means minus 2. X plus G. G means minus 1. Plus R. Root plus or minus. Plus or minus. R root 5 into root over 1 plus M square. Minus 2 whole square plus 4. So y plus 2 is equal to minus 2x plus 2 plus or minus root 5 into root 5. So y plus, here 2 cancel, y plus 2x plus or minus root 5 into root 5, 5 is equal to 0. So here we observe, we already find out the equation of tangent. 2x plus y minus 5 is equal to 0. ఇందులో 2x plus y minus 5 equal to 0. So another tangent equation 2x plus y ఇక్కడ minus 5 ఇక్కడ plus 5 is equal to 0. This is the answer. So students, we discussed once again I repeat, position of the point with respect to the circle and power of a point and length of the tangent, length of the chord and equation of tangent, slope form with the slope with M, and tangent, equation of tangent at point P. So to find out the position of point, what we have to find out? S11. Power of a point ki S11. Length of tangent formula root S1. Root S11. Length of the chord is equal to 2 into root over R square minus D square. Equation of tangent with slope form. Y plus F is equal to M into X plus G into X plus G plus or minus R into root over 1 plus M square. So equation of the tangent at one point S1 equal to 0. సో ఈ ఫార్ములాస్ ని యూజ్ చేసుకొని నేను మీకు హోంవర్క్ ఇస్తాను. సో చూడండి, ఫస్ట్ చూడండి పేజ్ నెంబర్ 30లో టెక్స్ట్ బుక్ లో పేజ్ నెంబర్ 30 ఎక్సర్సైజ్ 1B. ఫస్ట్ locate the position of point P with respect to the circle S equal to 0 when point and circling. సో ఏమి ఇచ్చాడు? పాయింట్ ఇచ్చాడు, సర్కిల్ ఇచ్చాడు, లొకేషన్, లొకేట్ ద పొజిషన్. ఏం కట్టాలి? S11 కట్టాలి. S11 0 అయితే ఏంటి? S11 లెస్ దాన్ 0 ఆర్ S11 గ్రేటర్ దాన్ 0 నా మీరు చెక్ చేసుకోవాలి. నెక్స్ట్ సెకండ్, ఫైండ్ ద పవర్ ఆఫ్ ద పాయింట్ P విత్ రెస్పెక్ట్ టు ద సర్కిల్ S ఈక్వల్ టు 0. సో ఇది కూడా S11 కడతారు. ఫైండ్ ద లెంగ్త్ ఆఫ్ ద టాంజెంట్ ఫ్రమ్ P టు ద సర్కిల్. ఫైండ్ ద లెంగ్త్ ఆఫ్ ద టాంజెంట్. ఏంటి ఫార్ములా? రూట్ ఓవర్ S11. If the length of the tangent, second Roman law, if the length of the tangent from 5, 4 to the circle x square plus y square plus 2ky is equal to 0 is 1. So ikkada root S11 is equal to 1. So root S11 1 కి ఈక్వల్ చేస్తే మీకు k వాల్యూ వచ్చేస్తుంది. నెక్స్ట్, if a point P moving such that the lengths of tangents drawn from P to the circle, so ఇది ఆల్రెడీ మనం చెప్పేసాం, PT1 by PT2 is equal to 2/3 అది. Next, if a point P is moving such that the lengths of tangents drawn from P to the circles, two circles ఇచ్చాడు, lengths of tangents are equal అన్నాడు. కండిషన్ ఈజ్ lengths of tangents are equal. సో ఏం రాస్తారు, PT1 is equal to PT2. సో ఇలా చేస్తారు. Find the finally the locus of P. సో ఇవే కాదు, ఎగ్జాంపుల్స్ కూడా చెయ్యండి, చాలా ఇంపార్టెంట్. ఎగ్జాంపుల్స్ ఎక్కువగా ఎగ్జామ్ లో ఇస్తాడు. పేజ్ నెంబర్ 43లో ఎక్సర్సైజ్ 1C లో ఫస్ట్ రోమన్ లోనే చేయగలరు. ఫైండ్ ద ఈక్వేషన్ ఆఫ్ ద టాంజెంట్ ఎట్ P ఆఫ్ ద సర్కిల్స్ S equal to 0 వేర్ P and S are given by. సో 4 ప్రాబ్లమ్స్. P 1 point and S circle. సో ఏం కడతారు, S1 equal to 0. సో టెక్స్ట్ బుక్ లేని వాళ్ళకి 1B 1C ఎక్సర్సైజ్ యొక్క ఆన్సర్స్ ఒకసారి చూడండి. అన్ని చేశాక ఆన్సర్స్ చూడండి. 1B ఎక్సర్సైజ్ ఆన్సర్స్ ఇవి, 1Cలో ఫస్ట్ రోమన్లో ఆన్సర్స్ ఇవి. ఓకే, థ్యాంక్ యూ.
Good morning, children. This is Sarita Vasan, English